right, folks. So, in the previous video, we talked about this definition of Beer's law, and we began to identify the variables. So we said A is for absorbance, and E is molar absorptivity or extinction coefficient. B is the path length, and C represents concentration. And we said the reason that we're doing this is because when we analyze samples or standards on the UV-Vis instrument, we have to make sure that we are making samples and standards that are in the working range of zero point 0.1 to 1.5. Anything outside of that limit, we just don't really trust. We can't put our full faith into that number because the machine is not made to distinguish the difference between super low and super high concentrations, right? So this is the sweet spot or the Goldilocks spot for the instrument. Not just for our instrument, but for almost all of the kind of general run-of-the-mill UV-Vis instruments, 0.1 to 1.5. So we talked about this concept of molar absorptivity, and we talked about this concept of path length. I want to talk about path length first because it's really kind of the easiest to understand. Again, we've got this instrument, and let's say there's my light bulb, and the light bulb shines on a sample holder, and some of that light comes through and it gets seen by the detector, right? I keep writing this description over and over because I don't want you to forget it. This sample compartment is very important. The sample compartment, or that sample holder, the sample holder has a specific term, and that is called a cuvette. Some people put the male pronoun on it, and some use the female version, cuvette or cuvette. Some end with a extra te. The female and male version in French, basically. So that is what we call a cuvette. We've got different types of cuvettes in a laboratory. That's what I put my sample into when I want to measure it. So if you hear us say, give us a cuvette, that's what we're meaning. These cuvettes are kind of rectangular in shape. That's why I keep drawing a rectangular box on the screen. But they can come in all forms and they can come in all sizes. But that is what we call a cuvette. The path length that's in this equation, that is representative of how wide the cuvette is. That's our path length. So the path length is how wide my cuvette is. Okay. All the cuvettes are standard. For the most part, when we run samples in a UV-Vis instrument, this is a 1 centimeter cuvette. Unless we do something kind of wonky on you, it's always going to be a 1 centimeter cuvette. Every time. Every time. And we promise that we will not do that for you. We will give you a 1 centimeter cuvette every single time. Everything will be made with a 1 centimeter cuvette. So you don't have to worry about the different sizes that are out there. And there are very many. You just have to remember one. So that means in this Beer's law equation, the B number will always be 1 every time. This is the number that I use for B. That makes my math much simpler because now A equals molar absorptivity times my concentration, because I can multiply 1 by anything and get the same number, so it really doesn't matter. So in a way, the B drops out of the equation when I use a normal run-of-the-mill cuvette that's given to me. So now instead of 4 variables to worry with, the equation turns into 3 variables. It kind of turns into A is equal to E times C. Again, B will always be 1 centimeter. And that's the number, or the constant, that I use into that equation. So now I've got to talk about this molar absorptivity number. You know, what does that mean? Okay, well, molar absorptivity is how hungry these compounds are. Certain molecules are introduced into the machine and they put a little bit of their favorite food onto a plate and they go and they eat it and they're happy. Other molecules go through the buffet line and they put a lot of their favorite food onto the plate and they go back to their table and they're happy. So the molar absorptivity gives us an idea of how hungry these molecules are. Okay? In other words, it gives us an idea of how much light they typically absorb based on some criteria that we set. So that's our molar absorptivity number. How hungry they are, or how much light they absorb based on certain criteria. The criteria here I don't want to go into. That's a little bit more advanced, right? If we just can accept the idea of molar absorptivity, we'll be okay. This molar absorptivity value, or the extinction coefficient, is a constant. But it's a constant based on each compound. So that means that it's a number that I should be pulling, and I should be putting that number into the equation. But I've got to realize what that number is in the first place, right? So there's tons of compounds out there, and there's tons of molar absorptivities out there, because there really is kind of a one number to one molecule type of relationship. All molecules have different hungriness, if that's a word, that they bring to the table. So what begins to happen is that I have to have a resource. I have to have some kind of reference textbook to pull this molar absorptivity number from. Okay, so the constant is particular on the compound. The constant I can get from the Merck, or from the CRC, or from the Sattler. Again, those are the 3 reference books that we have in our laboratory that we use to get this information from. This also had our lambda maxes that we needed for each compound, right? Those lambda maxes were listed, and molar absorptivities are listed as well. In these reference books, they are going to be listed with 1 or 2 variables. Some of the reference books will list the molar absorptivity with the E, the epsilon, just like it's written here into the equation. However, some of the textbooks will list the molar absorptivity as an A sub M. Both of those are the same thing. It really depends on the resource that you're pulling from. Some textbooks use epsilon to make it match the equation. Some textbooks use A sub M. Why A sub M? Because this stands for molar, M, absorptivity, A. Molar absorptivity number. So it will be a number. The number could be fairly large. The number could be fairly small. So let's say, for instance, that the molecule that we're running is 8710. 8,710. That is the molar absorptivity that is related to that compound. And that means that I need to be using that number in this equation when I begin to solve for a concentration in order to make a solution to run it on the machine. Okay, so if I want a one absorbance equals molar absorptivity for that compound, 8,710 times C, which is my concentration. So what I do is that I solve for the variable. I solve for C, right? So this is 8,710 times C. The rules of math say you do the opposite of. So if this is times C, I'm going to divide. What do I divide by? What I want to get rid of. 8710. So I divide each side by 8710. And that gives me C, which is the concentration that I need to be making. So if I pull up the calculator here, and we'll do it together, I can take one absorbance, and then I'm going to divide that by 8,710, and I hit enter. The concentration that I need to make is 1.15 times 10 to the, look at this here at the very end, -4. And that is molarity. Now that's where I'm going to stop this example. I can't weigh out molarity on a balance. I have to weigh out grams on a balance. So we're going to have to make the next leap eventually, and we're going to have to make it to that point where I feel comfortable converting molarity over to grams, and we'll do that together. But this is the first step in solving for that type of problem. So again, it's my job to make standards. Those standards have to be within a working range on the machine. In order to figure out how to make that standard, I need the molar absorptivity number, and that comes from the reference books. Once I know the absorbance that I want to make, once I know the molar absorptivity of that sample that I'm running, and if I assume that my cuvette is a 1 centimeter every single time, then I take my absorbance and divide it by my molarity, not my molar absorptivity, to get my concentration. So, shortcut here, take the absorbance that you want to make, divide it by the molar absorptivity of the compound, and that will give you the concentration that you need every single time, as long as you are using a 1 centimeter cuvette. All right. So that's the story with Beer's Law. That's the kind of background on the path length and the molar absorptivity number. This is a picture of the cuvettes that we have in the laboratory. They come in all shapes and they come in all sizes. This would be kind of the normal cuvette right here. So 1 centimeter wide, and your sample is poured into this rectangular shaped sample holder, and the plastic pieces just snap on top and they serve as a lid. We don't even use our lids, they're not needed. But they come in different sizes and shapes, and this one is meant to narrow down the bottom so you don't have to have as much sample to fill up. Some of these have rigid or cloudy areas on the side. Some of these are very narrow from top all the way up to the bottom. Here's another picture of some different cuvettes that may be out there. We see some that have these strange little tops on them. Some of these are specially made for gas samples and not liquid samples. Some of these, though, are larger, and these are really good for very weak solutions, and that's what you're seeing up here. So this is a cuvette as well. You would fill your sample full within this holder, and you would snap these caps onto the top, and that would go inside of the instrument. And of course, that is not a 1 centimeter cuvette, but you don't have to worry about those. You won't see those in the competition. In the program, you might. We might get you to do one of those just to give you experience with them. So in the next video, we'll continue on.